In mathematics, a simple group is a non-trivial group whose only normal subgroups are the trivial group and the group itself. A group that is not simple can be broken into two smaller groups, a normal subgroup and the quotient group, and the process can be repeated. If the group is finite, then eventually one arrives at uniquely determined simple groups by the Jordan-Holder theorem. The complete classification of finite simple groups, completed in 2008, is a major milestone in the history of mathematics. Examples: finite simple groups. The cyclic group G equals Z, 3Z of congruence classes modulo 3 is simple. If H is a subgroup of this group, its order must be a divisor of the order of G, which is 3. Since 3 is prime, its only divisors are 1 and 3, so either H is G, or H is the trivial group. On the other hand, the group G equals Z, 12Z is not simple. The set H of congruence classes of 0, 4, and 8 modulo 12 is a subgroup of order 3, and it is a normal subgroup since any subgroup of an abelian group is normal. Similarly, the additive group Z of integers is not simple. The set of even integers is a non-trivial proper normal subgroup. One may use the same kind of reasoning for any abelian group, to deduce that the only simple abelian groups are the cyclic groups of prime order. The classification of non-abelian simple groups is far less trivial. The smallest non-abelian simple group is the alternating group A5 of order 60, and every simple group of order 60 is isomorphic to A5. The second smallest non-abelian simple group is the projective special linear group PSL of order 168. And it is possible to prove that every simple group of order 168 is isomorphic to PSL. Infinite simple groups. The infinite alternating group, i.e., the group of even permutations of the integers, is simple. This group can be defined as the increasing union of the finite simple groups with respect to standard embeddings. Another family of examples of infinite simple groups is given by where as a field and it is much more difficult to construct finitely generated infinite simple groups. The first example is due to Graham-Higman and is the quotient of the Higman group. Other examples include the infinite Thompson groups T and V. Finitely presented torsion-free infinite simple groups were constructed by Berger-Moses. Classification. There is as yet no known classification for general simple groups. Finite simple groups. The finite simple groups are important because in a certain sense they are the basic building blocks of all finite groups, somewhat similar to the way prime numbers are the basic building blocks of the integers. This is expressed by the Jordan-Holder theorem, which states that any two composition series of a given group have the same length and the same factors, up to permutation and isomorphism. In a huge collaborative effort, the classification of finite simple groups was declared accomplished in 1983 by Daniel Gorenstein, though some problems surfaced. Briefly, finite simple groups are classified as lying in one of 18 families, or being one of 26 exceptions. ZP, cyclic group of prime order, and alternating group. For the alternating groups may be considered as groups of Lie type over the field with one element, which unites this family with the next, and thus all families of non-abelian finite simple groups may be considered to be of Lie type. One of 16 families of groups of Lie type. The Tits group is generally considered of this form, though strictly speaking it is not of Lie type, but rather index 2 in a group of Lie type. One of 26 exceptions, the sporadic groups, of which 20 are subgroups or subquotients of the monster group and are referred to as the happy family, while the remaining 6 are referred to as pariahs. Structure of finite simple groups. The famous theorem of Feit-Thompson states that every group of odd order is solvable. Therefore, every finite simple group has even order unless it is cyclic of prime order. The Schreier conjecture asserts that the group of outer automorphisms of every finite simple group is solvable. This can be proved using the classification theorem. History for finite simple groups. There are two threads in the history of finite simple groups: the discovery and construction of specific simple groups and families, which took place from the work of Galois in the 1820s to the construction of the monster in 1981, and proof that this list was complete, which began in the 19th century, most significantly took place 1955 through 1983, but was only generally agreed to be finished in 2004. As of 2010, update, work on improving the proofs and understanding continues. See for 19th century history of simple groups. Construction simple groups have been studied at least since early Galois theory, where Évariste Galois realized that the fact that the alternating groups on 5 or more points are simple, which he proved in 1831, was the reason that one could not solve the quintic in radicals. Galois also constructed the projective special linear group of a plane over a prime finite field, PSL, and remarked that they were simple for P not 2 or 3. This is contained in his last letter to Chevalier, and are the next example of finite simple groups. The next discoveries were by Camille Jordan in 1870. Jordan had found 4 families of simple matrix groups over finite fields of prime order, which are now known as the classical groups. At about the same time, it was shown that a family of 5 groups, called the Mathieu groups and first described by Émile Léonard Mathieu in 1861 and 1873, were also simple. Since these 5 groups were constructed by methods which did not yield infinitely many possibilities, they were called sporadic by William Burnside in his 1897 textbook. Later Jordan's results on classical groups were generalized to arbitrary finite fields by Leonard Dickson, following the classification of complex simple Lie algebras by Wilhelm Killing. Dickson also constructed exception groups of type G2 and E6 as well, but not of types F4, E7, or E8. In the 1950s the work on groups of Lie type was continued, with Claude Chevalier giving a uniform construction of the classical groups and the groups of exceptional type in a 1955 paper. This omitted certain known groups, which were obtained by twisting the Chevalier construction. The remaining groups of Lie type were produced by Steinberg, Titz, and Hertzog in 2E6, and by Suzuki and Rie. These groups were believed to be a complete list, but after a lull of almost a century since the work of Mathieu, in 1964 the first Janko group was discovered, and the remaining 20 sporadic groups were discovered or conjectured in 1965 to 1975, culminating in 1981, when Robert Gries announced that he had constructed Bernd Fischer's monster group. The monster is the largest sporadic simple group having order of 80801451287587559904971543680000000000. The monster has a faithful 196,883 dimensional representation in the 196,884 dimensional Gries algebra, meaning that each element of the monster can be expressed as a 196,883 by 196,883 matrix. Classification. The full classification is generally accepted as starting with the Veit-Thompson theorem of 1962-63, largely lasting until 1983, but only being finished in 2004. Soon after the construction of the monster in 1981, a proof, totaling more than 10,000 pages, was supplied that group theorists had successfully listed all finite simple groups, with victory declared in 1983 by Daniel Gorenstein. This was premature. Some gaps were later discovered, notably in the classification of quasi-Dean groups, which were eventually replaced in 2004 by a 1,300-page classification of quasi-Dean groups, which is now generally accepted as complete. Tests for non-simplicity. Louse test. Let n be a positive integer that is not prime, and let p be a prime divisor of n. If 1 is the only divisor of n that is equal to 1 modulo p, then there does not exist a simple group of order n. Proof: if n is a prime power, then a group of order n has a non-trivial center and, therefore, is not simple. If n is not a prime power, then every Solow subgroup is proper, and, by Solow's third theorem, we know that the number of Solow p subgroups of a group of order n is equal to 1 modulo p and divides n. Since 1 is the only such number, the Solow p subgroup is unique, and therefore it is normal. Since it is a proper, non-identity subgroup, the group is not simple. Burnside: a non-Abelian finite simple group has order divisible by at least 3 distinct primes. This follows from Burnside's PQ theorem.